Okay, so we are going to step into the idea of the different groupings and kind of some of their characteristic behaviors. The first group that we come across on the periodic table is the idea of the alkali metals, and they are soft, they're metallic solids. They come from the Arabic word for ashes, and it could be related to when sodium or sodium hydroxide came from when you basically ran water through wood ash, and you had this specific type of uh, you would develop sodium hydroxide out of wood ash, kind of percolating water through it. Okay, so your next slide here is on the alkali metals, but some of their behaviors, some of their characteristics here. So first of all, they are not found in compounds in nature because they're at least not in the elemental form, because they just are too reactive. And so they do have low densities and low melting points, as you can see from the table here. Okay, and you notice their electron configurations. They all have one electron in the outer shell. And lastly, they have low ionization energies, meaning to remove one electron out of their outer shell does not require a lot of energy in the process. And they are known to react vigorously in water, and this is kind of in order from lithium, sodium, and potassium, kind of in order of photos. And things to note about alkali metals. So when they react with oxygen, they form peroxides, okay, which a little different than most things. So that's one of the reasons why alkali metals are stored in oil, but they are, because they react with oxygen in the air, they tend to not do that. So potassium, rubidium, and cesium also form superoxides, so like KO2, and they produce bright colors when placed in flames. So when you do flame tests with alkali metals, you get really distinct colors from them. Next group is the alkaline earth metals, and they have they have higher densities, higher melting points than the alkali metals. So we're kind of moving up as far as kind of that second electron in the outer shell, and their ionization energies, although are low, they aren't as low as the alkali metals. So it's still easy to remove 2 electrons or move that outer electron out of it, but not as easy as with the alkali metals. The alkaline earth metals react with water, but it's definitely not as vigorous as the alkali metals, for sure. And reactivity tends to increase as you go down the group. So as you go down the group, things become more active, the same way that the alkali metals behave. Okay, group 6A, so that's going to be your oxygen, sulfur, selenium, tellurium, polonium, the chalcogen group, or it's CHALOGEN. I'm not quite sure where that naming comes from, but I've seen it referenced before, and I think even your textbook references it. But some things to note about it: oxygen, sulfur, and selenium aren't metals; they're non-metals, and so their melting points are pretty low for those substances. Tellurium is a metalloid. Polonium is radioactive. So very unique kind of grouping. One thing to note about oxygen, which is in this group, has 2 allotropes, and an allotrope is, so the elemental form of oxygen can be either O2 or O3, and O3 is really important in the stratosphere, but which is the layer above the layer that we live in. So we live in the troposphere of the atmosphere, and then there's the stratosphere up above. Ozone is really important layer in the lower part of the stratosphere because it kind of absorbs a lot of high energy radiation that comes in from the sun and does a chemical reaction by absorbing that energy. We'll talk about that in class. And there can be 3 anions of it. So you've got the oxide, you've got peroxide, and then you've got superoxide. So that's just where, notice the charge related to two oxygens bonded together and they have a -1 charge. So a couple different ways that oxygen can be different or unique. And it tends to take electrons from other elements, so it oxidizes, oxidation, right? So thinking of redox reactions. All right, sulfur is a rather unique compound as well. So its elemental form is S8, and it's a weaker oxidizer than oxygen, but it will do that. Its most staple allotrope, or the elemental form of it, is S8 in this ring molecule that's here. Okay, and then we move into the halogens. Halogens, as you know, so most of them are gases at room temperature, uh, and so very low melting points, and their densities are kind of vary across it. But really high ionization energy. It takes a lot of energy to remove remove electrons, and they're your prototypical nonmetals. So when we talk about nonmetals, we are talking about halogens because they behave very much like a nonmetal. And halogens comes from this idea of salt formers because halogens combine with metals to form salts. That's the classification of a salt is something combined with a halogen, and that's always going to be metals. Metals combined with the halogen. So some of the characteristics, they have large negative electron affinities, meaning the pull for one more electron is really strong. So they tend to oxidize other elements really easily, and they react directly with metals to form metal halides or salts. And chlorine is added to water supplies to serve as a disinfectant, and that's just kind of one of the notes. And actually, so chlorination of water is a common practice, but I've even heard of bromination of water as well. Noble gases, we've talked a little bit about them in the past. So it takes a lot of energy to remove an electron out of a noble gas, and so it's not very common. And electron affinities are positive, meaning that they tend not to want or draw in electrons. So this kind of leads us to this reality that noble gases, for the most part, are pretty unreactive. And they're always found as monatomic gases. So they aren't bonded with other things. It's just single atoms, unbonded, unreactive. Now, some of the larger noble gases can form some compounds, which they've discovered, which is actually really was kind of an interesting discovery. So xenon can form a couple compounds with fluorine. That's really on a part of the fact that fluorine is so reactive that it's reactive enough that it'll combine with xenon, which is very unreactive, but it's strong enough to kind of start pulling and sharing those electrons. And krypton forms one stable compound as well. Oh, and then you have the unstable H argon fluorine was synthesized in 2000, but with limited application in the long run. So that's it, and I will see you in class tomorrow.